Hello guys, welcome to this new video. So now we're going to go through question 6 in the May 25 Specimen Paper 2. So here we have a long text about how a smoke detector works, just based on some alpha decay. And we're also told the decay constant of one of the substances that we could use and the dimensions of the chamber. It's not so important at the moment, but in the first question, we need to complete the nuclear equation for this decay. So we are told that this nucleus of americium 241 has 146 neutrons and it decays into an alpha particle or using an alpha particle. So we know that the mass number is 241. So that always goes up here. And this is the proton number. So the mass number is just the number of neutrons plus the number of protons. So from this we can calculate the number of protons. This is just the difference between these two. So we have 95 protons. And well, we know that an alpha particle has two protons and two neutrons. So a mass number of 4 and a proton number of 2. And we know that these have to be conserved. So the proton numbers and the mass numbers should add up to the same thing on both sides. So we need to have a 93 here, as 93 plus 2 is 95, and similar logic 237 over here. And we need to outline why the radioactive source is safe for using in-house. Well, as you can see, we use an alpha particle. We use alpha particles, or we produce alpha particles, which are they are really not that dangerous. They only travel a few centimeters in the air. They have a very small penetrating power, as they can get ionized very quickly due to their charge. So only travel a few centimeters in the air. So they really cause no harm. Then we need to deduce whether this radioactive source will need to be replaced. Well, probably the easiest way we could solve this is if we consider the lifetime of the source itself. And a way we can measure the lifetime of a source is using its half-life. So how much time is required for the activity of our source to halve, as then it will not be so efficient anymore, then we might need replacement. And well, we know that the half-life can be calculated with this formula. It's in our data booklet. And we know the decay constant, that's the lambda over there. It's this number over here. So our half-life will just be ln2 divided by 5.08 times 10 to the minus 11. So our half-life is 10 to the 10 seconds, which if we convert to years is approximately 430 years. This is, well, as you can imagine, this is really long. And it's very likely that other components in our smoke detector would need replacement before the alpha particle, the source. So for 430 years is much longer than the expected life of our detector, so we will not need to replace it. So much longer than life of detector. So no replacement is needed. And then we are told the initial activity of our source. We're told that only 33% of the alpha particles form an ion pair. We're given the energy of one alpha particle, and we also have how much energy is needed to form an ion pair. And we need to calculate the maximum current in the chamber due to the electrons. So we firstly need to, well, if we calculate the amount of charge we have, then that's already kind of the current we will be having. So we need to somewhat determine how many ions are being formed. So we know that one alpha particle produces, well, if one alpha particle has an energy of 5.5 times 10 to the 6, and for one ion pair we need 15 electron volts of energy, Then from one alpha particle we will form 3.6 times 10 to the 5 ion pairs. Now we need to see how many are being formed per second. We know that our initial activity is 42 kilobecquerel. And technically this becquerel just means 1 becquerel is the same as 1 decay per second. So if we want to calculate our ions per second, what we can do is multiply this 3.67 times 10 to the 5 by our activity, so that we can see how many decays we have in 1 second, and we only know a third of our alpha particles actually produce an ion, so we still need to divide it by 3. So this will give us 5.13 times 10 to the 9 ions per second. And well, we know that current is the rate of flow of charge, like this. And well, we already have this per time aspect as it's in per seconds, but we only have the number of ions, so the number of electrons we have. And if we want to know the charge of all of these, we still need to multiply it by the charge of one ion, which is just 1.6 times 10 to the minus 19. So we need to still multiply this with E, 1.6 times 10 to the minus 19. This will be a current of 0.82 times 10 to the minus 9 amps. And so this will be in coulombs per second, or in other words, amperes. And well, this was the end of question 6. I hope I was able to help, and see you in the next video.